This first video of Module 5 is on protecting groups, including acetals and ketals, although acetals and ketals serve other functions rather than only as protecting groups. We start with this famous example of the use of protecting groups for the synthesis of the molecule palatoxin. Look at this complicated molecule. This is a natural product. And notice how many hydroxy groups it has. It's from the coral of the genus Palathoa and one of the most poisonous substances known. Its synthesis and structure elucidation needed to be done simultaneously. So even all our NMR work couldn't figure out the structure, especially with all the stereochemistry. Look at all the different R or S configuration centers. And when the molecule is synthesized in the animal, it's made precisely at all those stereocenters, amazingly. A lot of marine natural products are not truly from the organism they seem to be from. So corals, sponges, and things like that have a lot of symbiotic organisms, and many of these products could be bacterial actually in origin. So not actually from the animal itself. The need for protecting groups was seen in the synthesis of palatoxin, but I'm going to show a little bit more on that later. First, we'll take a look at some simple examples like the protection of alcohols. So for example, if this is your target molecule, notice it has two alcohols. And let's say that you propose a retrosynthesis from a Grignard reagent here, reacting with ketone. Actually, it's the molecule acetone, if you look closely. And then you figure that these electrons will go and form a bond to that carbonyl carbon, leading to the product with the formation of this bond. You would prepare that Grignard reagent from this molecule and magnesium metal. However, there's an issue. As shown here, this magnesium bromide, this Grignard reagent, can react with itself very easily. And this proton here on the other end of the molecule is fairly acidic, meaning it can be removed fairly easily. And so this is self-reacting, and unless you have it in large excess, you're losing all of your reagent as soon as it forms. So the strategy then, the solution, is to protect one of the alcohols. The alcohol on the left will be protected through this scheme. And so we haven't seen this before. This is trimethylsilyl chloride, or TMS chloride. TMS chloride. It's a silicon, notice, not a sulfur. The electrons on oxygen can go and actually fit in here because of the size of silicon, much larger than carbon, and you can kick off that chlorine in SN2 style, and the size of silicon allows one to overcome the fact that it's tertiary, fully substituted. So it enables that to come in. That results after deprotonation on the end of this oxygen, results in an OTMS, protecting group. So that's a protected alcohol. Now the protected alcohol can be used to make the Grignard reagent here and here from that process. Now the Grignard reagent can go and form a bond with that carbonyl carbon, creating this new carbon-carbon bond right here. And then deprotection under similar conditions usually gets the alcohol back intact. So that's the concept behind the use of protectant groups in a fairly simple example, although we did see a new thing here. The trimethylsilyl group has its uses in other ways too. It's actually very non-polar, and it can be used to change all the polar OH groups of, for example, a sugar. You can change them all to OTMS groups, and the sugar then becomes completely non-polar instead of polar. And a lot of times we do things like that in order to separate it from something else, for example, in separations or chromatography. Now, I've talked about palotoxin before. You've seen one simple example of a protecting group being added and removed, deprotected. Now take a look at this step in the synthesis of palotoxin. In that project, look at all the protecting groups. And in fact, this project was amazing in other ways in that they had to invent new protecting groups in order to cover their bases all the way through the synthesis of this molecule, as they went from, I believe, left to right, basically, synthesizing fragment after fragment with many multiple steps of protection. And then notice this, toward the end of their work, in a fairly short sequence, although this looks like a lot, and we're not going to go into these details, they deprotect everything. And so I think that was part of their strategy, their amazing, strategy to take on the challenge of this synthesis. This wasn't quite the final product, but it was getting close, very close already. So imagine that the amount of work, and many, many years of work by many, many people. We will look at protecting groups for carbonyl groups. So how to disguise a carbonyl and do chemistry elsewhere in the molecule, disguise or protect the carbonyl, do chemistry elsewhere, and then go back and deprotect. So before we really get into the main part of that, I'm going to just show you this simple example of the addition of water to a ketone. So we have bond formation there, leads to this new bond here. Add a proton here, remove a proton there, and you end up with this product. We call this a hydrate. It's not quite the same as an acetal or ketal, but really it does have the same sort of electronic setup. It's just that it has two OHs. Compared to the original carbonyl, it's been hydrated. You've added H2O across the carbonyl, across what was the carbonyl technically. So hydrate's a pretty good name for this. Now, in acidic conditions, a carbonyl group, and let's start with an aldehyde here. Carbonyl group can be protonated, so now this is an activated carbonyl, as we've seen before. Makes the carbonyl carbon even more electrophilic to a nucleophile, like the oxygen of methanol coming in here. Kick those electrons up to the plus charge, brings us to this intermediate deprotonation, brings us to the hemiacetal. And acetals are those that result from aldehydes. Ketals result from ketones. Now, the sequence can continue with protonation here, and all these are actually reversible in the deprotection. Protonate there, now you have this intermediate. You can bring electrons down to this bond here, kicks off this fantastic great leaving group. Now you have this all primed and set up for a second molecule of methanol to come in here. Second molecule of methanol comes in, kicks those electrons up. I left off a plus charge there. Oops, right? Got to always reassess formal charge. Gets us to this intermediate. Deprotonation gets us to the acetal, which you can see the old aldehyde in there because of the aldehyde, what was the aldehyde proton, what was the aldehyde carbonyl here, now protected. Protected carbonyl, protected aldehyde. In the same way, and with the exact same steps, you could take a ketone. So I just drew the same thing, only now it's a ketone. That leads to the corresponding similar compounds, hemiketal, ketal. In every other way, the series of reactions is all the same. So you could try this sequence out in similar way to the one above. All four, meaning the formation of the hemiacetal, hemiketal, acetal, and ketal, or hydrate for that matter, all four are reversible back to the original aldehyde or ketone during your deprotection. If it wasn't, we wouldn't be talking about this. So it's reversible. It can be deprotected. The reason that they had to invent new protecting groups in the multi-step synthesis of palotoxin was because the deprotection conditions sometimes affected and deprotected more than they wanted to at a certain step. So they had to have a different protecting group that didn't get deprotected under those conditions, and so on and so on and so on with all those OH groups. Here's another example in synthesis similar to the one we had above. Let's say this is our target molecule. I apologize. This is our starting material. I'm going to leave that in the video for posterity. There you go. Rather than reshoot the whole video at this point, I'll admit it. Say that you want to do a reduction reaction here on the ester and not on the aldehyde. These are pretty similar functional groups, and in fact, a reducing agent like a hydride will react with both the ester and the aldehyde. So let us protect the aldehyde with an acetal. Acidic conditions in methanol, same steps as we did above. Now it's protected as an acetal. We do the hydride reduction with lithium aluminum hydride. That's actually going to add H minus twice, the equivalent of H minus, right? Always have to sort of stipulate that. It's going to add once and in a series of arrows kick off this group. Then it's going to add again. Ultimately, you get the addition of 2 hydrogens here. We're going to see more of that in the next unit, actually. We're going to do more chemistry of esters and things like that. So this ester has been reduced. It's a reduction. Hydrogens have been added. Oxygens have been removed. That's reduction by any definition. Now you can deprotect the acetal. Get your aldehyde back. And you manage to do a reduction on one side of the molecule without affecting the other side. So there's a whole lot more we can do with this. We're going to do some more exercises in class and so on. Let's have one more example. Here's what I meant to do earlier. This is our target molecule, a new target. Let's say we want to make this. And it is very similar to the one way above earlier in the video. So our retrosynthesis says we can make this from a Grignard reagent to create this bond here, and we visualize a carbonyl group here where this OH is. Backwards thinking, right, to this. So the arrow pushing, we presume, would be the Grignard reaction in this way. Okay. However, we can start with this molecule right here. It's got the aldehyde on one side, an alkyl halide functionality on this side. Acidic conditions with methanol, like we saw above, we protect the aldehyde. Now it's protected. Why? Because otherwise the aldehyde is susceptible to the Grignard reaction as well. So this can self-react if the aldehyde is not protected. So we're going to protect the aldehyde here, protected aldehyde. Now we can make the Grignard reagent here, add our magnesium metal, metal disappears, inserts, we create this carbon nucleophile here, protected aldehyde, react it with acetone, ketone, in the same way, quench it with water, we get this new bond forming from the Grignard reaction. We deprotect the acetal back to the aldehyde. Now we have achieved our target. All right, so acetals and ketals. We also brushed on a little bit of protecting groups for alcohols with the trimethylsilyl group. We won't do a whole lot more of those. But we will do a lot of arrow pushing related to the acetal and ketal chemistry.